Okay, so we're going to take a look at some more on logarithms. Okay, and we're going to apply them to some real life stuff. So let's do this. So we're going to do logarithms applied using them for modeling. Okay, they don't have a lot of applications, but I'm going to show you a couple different things, and we're going to solve some equations. I should say we're going to solve some exponential equations. Okay, so let's take a look at some stuff here. So, first of all, let's talk about solving exponential equations first. Okay, get that out of the way. Okay, so let's say we have a basic little exponential equation here that we need to solve. All right. We could graph this, right, and figure out where the intersection is. Graph this part, find the intersection. Guess and check, obviously, we could try that too and get it. But one thing that we can do, when we have a variable in the exponent such as this, then what we can do is take the log of both sides. So I'm going to take the log of this equals the log of that. When we do that, this x is going to pop down in front using our properties of logs. All right, and now we can just divide. So now I would just take the log of 10. So let's see, I can jump into decimals, I think, and do that. Here we go. So let me go into decimals to do that. So I'm going to go to functions, miscellaneous log. Okay, so we're going to take the log of 10 divided by log 3, and there it is. Okay. So anytime we have a variable in the exponent, we can log both sides. It becomes very simple. So let's try a couple more here. Let's say it gets a little bit more complicated. Something like this. Let's put the plus 5 up top. All right. So again, we're going to log both sides. Okay, this 2x is going to pop out in front. And we can use any base, but I'm just using the common base here. Divide by the log of 3, divide by the log of 3. Log of 100 is 10. And then I'll use my decimals again. 20.95. All right, and then just finish it. So, I mean, you know, you could go ahead and oops. So 7.97. All right, so those are just kind of a couple of examples of where You can take, when you have a variable in the exponent, you take the log of both sides, use that property of logarithms. Works out pretty slick. Okay. Obviously, you can just graph it too, so you're going to have a little bit of both on that. All right. I want to get into some modeling a little bit with logs, and there's a couple of applications. One of them has to do with earthquakes, of course, and you probably did some of this last year because, all right, decibels and pH are the three things that have some with logs, obviously. So earthquakes, when you hear about the Richter scale, all right, the Richter scale, if you hear, say, you have a earthquake with a Richter scale of 4, okay, so they had an earthquake and the Richter scale measured 4, all right, and then somewhere else you hear maybe one has a 6, okay, so you might say, well, that's just a 2 and change of earthquakes, but what does it mean on a Richter scale? Well, the Richter scale measures earthquake intensity, all right, so it's hard to really get a feeling for, well, what is an earthquake, a Richter scale of 4? So if we asked, say, Richter scale 4, yeah, let me put my keyboard in here. Okay, so let's see. Richter scale right there. All right. So if I have a Richter scale, say, of 4, what exactly does that mean? Well, it says that a Richter scale of 4, right, if we look at Wikipedia or so forth, but let's see what this says. Earthquake magnitude scale and classes. So 4 is a very light sort of an earthquake, all right? So 4 would be often felt but only causes minor damages, all right? So that's what that would be, okay? So you feel it but not that big of a deal. Whereas 6 means slight damage to buildings and other structures, okay? So 6 would be considered a strong one. So 4 to 6 on the Richter scale basically talks about intensity. Since this difference is 10, we would say that it's 10 to the second times more intense. And since it's dealing with a power of 10, that means that it's logarithmic, all right? So if we take the log of 10 to the second, obviously, that 2 is going to pop out in front, right? And we know that this is a base 10. Again, we're using a common log. So this is going to be 1. So, ta-da, there's our 2, right? So that is application of logarithms, in that even though this is a 2, we call it a twofold change, it's actually 10 to the second times more intense, all right? So again, going back to that, all right, if we had one that was, say, 3, which, we don't really feel at all, versus one that's a 7, all right, so from a 3 to a 7, well, that's 4 changes of magnitude, or 10-4, so that would be 10 4-fold, so that would be quite a bit more intense of an earthquake, all right? And looking at this, you can see that it goes from often felt with minor damage to a major earthquake with serious damage, all right? So that's an application of logarithms, is the Richter scale, all right? Decibels, we're going to do one here in a second. pH looks at ion concentration. So those of you that had some chemistry background, you've done some stuff with pHs. I know Mr. Ford works with you on it, okay? So if you take hydrogen ion concentration and you want to find the pH of that, then you would take the log of the hydrogen ion concentration. I think that's OH. And if you make it negative, that will tell you the pH of that liquid, whatever it is. Okay, so that is a logarithmic application. All right, so I think in the book it gives a couple of examples of some hydrogen ion concentration. Let's take a look here and see. Yeah, it's on page 325, and it talks about the hydrogen ion concentration. All right, so it says a hydrogen ion concentration of vinegar versus baking soda. All right, so the vinegar, it says, has a pH of 2.4, which means that, here, let's go down over this way. So this is example 6 on 325. So if you have, say, some vinegar with a pH of 2.4 and some baking soda with a pH of 8.4, right? The difference in pH values is 6, but the difference in the hydrogen ion concentration is going to be 10 to the 6th, all right? Because it's 6 times more, tenfold, in other words, 10 to the 6 times more ion concentration, all right? So anytime you have a power like that, it's going to be a pH. So there are some applications for logs. Now, one other thing that does come up in some science classes, so I want to go into Desmos and just go ahead and log into my account. You should know what that is by now. And we're going to look for a graph called decilog right there. And here it is. So what this is on the x1, those are decibels, and y1 is the intensity of decibels in someone's ear. And I'm not sure what the what the units is, but you can see at 0 decibels, there's not a whole lot of intensity. And at 20 decibels, which is really, really soft, if you look that up, you can see what that is. So 20 decibels. Let's look that up. 20 decibels. Okay, so you can see here it says library bird calls are 40, 40, 44. Pretty light, quiet rural area. 30 whisper, rustling leaves is 20 decibels. So that's pretty quiet, and you don't hear a whole lot there. So what we're going to do then is take a look at some decibels with logarithms. So I'm going to go back to my decilog thing here, and I'm going to graph this. So let's see, I'm going to type these in. Let me put this on projector mode so you can see it. All right, and so we should pause this so you can type these numbers in. Okay, so hopefully you're unpaused and you got these numbers typed in, and we have a graph down here. Now, I had to make sure that my window was right, okay, because you're probably not seeing things very well if you just use the standard window that it comes with. So I made my x-axis, all right, start at 0, and my x-axis ending point is 200. And my y-axis, I want to make 0. And my y-axis ending point, let's see, I've got a big number here. 1, 2, should be good enough. Okay, so let's see what we got. We've got that. Maybe I went just a tad bit too big. Let's see, I need 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this one doesn't need it. This one can be 0. Okay, let's see what we got here. Okay, so we got 1 point here, and that should be 180. I'm missing the 180. It must be right up there someplace. Okay, it's not showing up. Whoops, this thing keeps messing up on me. So I got 50, 60. Oh, guess that is 80 right there. Okay, so there it is. All right, maybe I want to change this just one more time. Sorry, to get this to where I want it. Let's go with 2. 1, 2, 3, 4, 5, maybe. I want this to be just what I'm trying to get for you guys. There, perfect. So on this graph, we notice that we have this like straight line, then all of a sudden it shoots up, right? But these numbers are so off, they're so very, very small to very, very large, that it's hard to get a feeling for what this graph really looks like. We know that it's going up, but it's really hard to get a feeling for it. So when you have numbers that are such extreme in cases, it's also very hard to find any type of an equation that models that. So what we're going to do is do something called a logarithmic graph, a semi-log graph on this, to make it look a little prettier. So we're going to go over here to this next column. There we go. And I'm going to type in the log of y1. So I'm going to go y1. Now when I do that, I get a much different graph here. All right, now I'm just getting this straight line. So let's undo this. And now let's adjust our window so that it fits better. All right, so let's go back to this. So I'm going to go 0 to 200. And let's see, I've got a -8. That looks pretty good. So -10 to 10 might not be too bad. Let's try that out. -10, and we'll go to about 10 here. Okay, so there it is. All right, now this is a much better graph. You go, oh, hey, that's just a nice line, right? Okay, so we can do that. The problem is that it won't find a regression for us because of it's not set to an actual variable here, like y1. It's set to a log of y1. So we have to do it the old-fashioned way, right? So let's find y equals mx plus b by looking at the slope. All right, so I'm just going to pick the slope between 2 points. Actually, we'll do the slope between the last two and the first two. So this is going to be -9, basically, to 4. So that would be a change of 13. So I'm going to come down here and go y equals 13 divided by, now I need a change in the x, that would be 180. Okay, x minus, since I have 0, I know that it's -9. And ta-da, there is a fit. Now that's pretty dang good. All right, I could adjust it maybe a tad bit, but it goes through most of those points. That looks like a pretty good fit. So there's my equation. Y equals 13 over 180x plus, minus 9. But in this situation, the y value represented the log of these. So what I'm going to do is I'm going to have to put this in here. All right, so now I have, that's my real equation. Remember that this base here is 10. So really, I can apply the definition to this. So I'm going to go 10 to this power is equal to y. So now I actually have an equation that represents the data that we had originally. Okay, because I took the log of those nasty numbers, all right, found an equation for it, a line that fit it, substituted the log of y back in for y because that's what y represented. It represented that log of y, right? And then I just went ahead and used the definition. So I went 10 to the this number equals y. That's my definition. All right, so now I have that. So if I go back into this, okay, I'm going to type this in now. Y equals 10, okay, to the, and I have to put a parentheses or else it doesn't work, to the, let's see what that was, 13 over 180. Oops. Let's try this again. 13 divided by 180 x minus 9. Is that what it was? Yeah, it's right there, right above me there. There it is. Okay, now let me go back up. Turn this on and look at that. Okay, so that's pretty good. I mean, if we kept going, we'd see that it's actually going to fit all the other points. Also, there's one more there. Okay, so pretty cool. Right? That's called a semi-log graph because you're taking these nasty numbers and you're taking the log of them. It is possible to have two sets of nasty numbers and then you have to do a log-log graph, but you don't see that very often. Okay. So that was pretty much what I wanted to show you about logarithms. And then Monday, we'll take a look at some money stuff, which won't take very long. I just wanted to show you a couple things with that. And then we'll be ready for our test on Thursday. And we'll probably take a little bit of time Friday to finish it if you need to. But that's kind of the plan for next week. So let me give you an assignment here to work on. So on page 331, we're going to do numbers 11 through 18. Okay, which is basically having you solve the equation algebraically. So you would use the log of both sides. And then you don't have to substitute it back in. You can just come up with an equation. I'm not interested in you substituting it back in. 28 through 34, which is, I believe, some more solving equations. Now, some of those are pretty tricky, so you may want to graph those rather than trying to do some log stuff. 29 and 30, I would definitely want to try graphing those because they're a real bugger to do otherwise. But there are some pretty interesting log equations there. 41 through 43 talks about how many orders of magnitude. So that would be how many powers of 10 you would have. So it's that fold. So like here where we had the earthquake that went from 3 to 7, the orders of magnitude would be 4 because that's the difference there, or 10 to the 4th. And then 45 and 52. And 52 talks about a Newton's law of cooling thing. Kind of interesting, I guess. Some of that stuff you've probably done. So anyway, there are some problems for you to work on. Okay. Actually, then I think you're going to finish your quizzes. So I got those set up for you. So you should work on this for a bit, finish your quizzes, get those done, so we can get that taken care of. Otherwise, we'll see you on Monday.